My name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my series of lectures on the course DC Machines and Transformers. In my previous lecture, we have discussed in detail the construction details of DC generator. So in today's lecture, we are going to discuss the working of DC generator. So here we can discuss the working of DC generator in two methods. So first we'll see method 1, then we are going to see method 2. In method 1, we are going to utilize the principle of dynamically induced EMF. So that we call it as E is equal to BLV sine theta. That is the expression for dynamically induced EMF. Okay, so first let us consider for our easy understanding only two poles, that is north pole and south pole. Okay, the blue lines that are indicated are the direction of field, so they will never change, they will always from north pole to south pole. For our easy understanding, I have considered only one conductor which is in this position. So as shown here, this is the conductor. So let us assume initially that the conductor is in that position 1. So when the conductor is at that position, you can see the velocity component will be in this direction. So the velocity component will be in this direction, and the field direction will never change. It is always from north pole to south pole. Since both are parallel to one another, the angle between them is 0. So according to my EMF equation or dynamically induced EMF equation, BE is equal to BLV sine theta. Since theta is 0, sine theta is also 0. So in that position my EMF is 0. So assuming that the machine is rotating in clockwise direction, after some time the conductor will come at position 2 as shown in the diagram. So in this position my velocity component will be in this direction. Okay, so the field direction will never change and the velocity direction is in this direction as shown, and let us assume that there exists some angle between them, theta, and that theta angle will lie between 0 and 90, somewhere in between. So in this range we know that theta sine theta is positive. So according to my expression of E is equal to BLV sine theta, my value of EMF when the conductor is in position 2 is positive. Coming to the third position, so in this position anyhow the field direction will never change and the velocity component will be exactly 90 degrees when with respect to my field direction. So since theta is equal to 90, we all know sine 90 is 1. So in that position, according to my expression E is equal to BLV sine theta, so my magnitude of EMF in this position will be positive maximum value. Next, when the conductor comes to this fourth position, you can see the field direction as usual will never change and the velocity component will be in this direction and the angle existing between them will be in between 90 and 180, somewhere in between 90 and 180. So again theta is positive here, sine theta will also be positive. So according to my dynamically induced EMF, E is equal to BLV sine theta expression, my E will be, that is EMF value will be some positive value. Yeah, next in position 5 you can see the velocity component and the field component directions are exactly 180 degrees. Okay, quite opposite to one another. So we know that sine 180 is 0. So according to my expression, E is equal to BLV sine theta. My magnitude of EMF will be 0 in position 5. So when the conductor comes at this position, you can see field direction obviously will not change. The velocity component at this position will be somewhere here in this direction, and the angle existing between them will be somewhere in between 180 degrees and 270 degrees. In this range, we know that sine value is negative, so therefore EMF induced at this position will be some negative value. And in the 7th position, the angle existing between velocity component and field component is 270 degrees. So sine 270 is minus 1. So therefore in this position, according to my expression, E is equal to BLV sine theta, it is negative maximum value. And again in position 8, the angle existing between velocity component and field component will be somewhere between 270 degrees and 360 degrees. And here again the sine value is negative. So therefore according to E is equal to BLV sine theta, the magnitude will be some negative value. And my next position will coincide with my first position. So in summary, when I put all this together, we can observe we have got in position 1 EMF is 0. In position 2, my EMF was some positive value. We do not know the value, but some positive value. So here is some positive value. In position 3, I got positive maximum value. In position 4, my EMF was again some positive value. In position 5, my EMF was 0. In position 6, my EMF value was some negative value. In position 7, my EMF was maximum negative value. Again at position 8, it was some negative value. And this coincides again with my first position. So from this analysis, as I told you in my previous lecture also, the output of my generator is always alternating in nature. So in order to convert this alternating in EMF, we have used commutator. That is what I have discussed in my last lecture. So that is what is the working of DC generator. So we can also analyze the working of DC generator using my second method, that is as a simple loop generator. So let us consider this is the overview of my single loop generator, where I have 2 poles for simplicity, and I have assumed my armature to be a single loop. Let us consider when the single loop generator is at position A. So you can see 1, 3. So we are going to analyze in positions 1, in 1, 3, 5 and 7. So in all the 4, you can see in all the 4 positions we are going to analyze my single loop. Okay, mind you, remember that here I have one conductor and here I have one conductor. Okay, so in my single loop I'll have 2 conductors, and my 2 conductors are present here, as you can see. Okay, so in this position there is, you can see the plane of the coil is exactly to the right angles of my flux lines, and the flux linking with the coil will be maximum, but rate of change of flux linkages will be minimum. Hence in this position my EMF will be 0. So in position A, my EMF will be 0. So again, when I rotate this through some 90 degrees in position 3, at position you can say B or 3, exactly when it is rotated 90 degrees, again I need to remind you that here I have one conductor, here I have one conductor. Okay, so in this position you can see as I rotated the coil from 0 to 90, the rate of change of flux linkages will gradually increase. So therefore the induced EMF will also increase. So here you can see that uh, since the plane of the coil is exactly parallel to the flux lines, so here the rate of change of flux linkage will be exactly maximum, okay. So since rate of change of flux linkages are maximum, the induced EMF in the coil will also be maximum. So here the position B, my EMF will be in maximum value at 90 degrees. When I again rotate to 90 degrees, that is from 90 I have rotated till 180 degrees. In this position you can see again we will get the same result as the first position because both are in the same position. Here also the plane of coil is exactly 90 degrees to the flux plane, isn't it? So the rate of change of flux linkages will gradually decrease from initial position, from the previous position I mean. So therefore EMF also will gradually decrease, and in this position it will become 0. So at position C, my EMF will be 0. So again when I rotate the coil through 90 degrees, so here you can see if I go back in position A, B, C, the coil was under the influence of south pole, isn't it? Now in this position that same conductor is coming under the influence of north pole. So therefore obviously the current direction will change. EMF induced expression or magnitude will also reverse. In this position also it is same as the position 3, or you can say B position. So here the plane of coil is parallel to the flux plane, so therefore the flux rate of change of flux will be maximum. Okay, so in this position even though it is maximum, the current will be in opposite direction, thereby the magnitude of induced EMF will also be in negative direction but maximum value. So you can say at position D my EMF will be maximum but negative value. And coming again, so it will again resume 360 degrees is same as 0 degrees. So here also no EMF will be induced as the plane is exactly to right angles to the plane of flux lines. So no EMF will be induced in this position. So from our analysis you can see the EMF induced will be alternating in nature. So this is a small animation illustrating how upon rotating of my coil gradually my EMF induced is increasing from 0, and exactly at 90 degrees my EMF is maximum, and because it is maximum change in flux that occurs there. So again at further when I increase and rotate by 90 degrees, you can see gradually my EMF is returning, gradually decreasing, and it becomes 0 at T/2. So again further if I rotate, since my current is reversing, my EMF magnitude also will reverse, and at 3T/4 my magnitude becomes negative maximum. Okay, and again if I further rotate by 90 degrees, you can see the EMF will slowly return back to 0 at time t. So that you can see, observe the galvanometer also, how initially my value was positive, it was returning to 0, and again it is going to negative and returning it to 0. So this is a small illustration of how my EMF is induced in a simple loop DC generator. So as I told you that I need a commutator, because since this is a generator, even though my output is alternating in nature, so I need to convert this into a unidirectional EMF. Okay, so there comes my commutator. So before we see in detail the action of commutator, I just want you to listen this a small video regarding the commutator.
We need only keep the coil rotating in the magnetic field to continuously induce electric voltage and current. But current produced in this fashion has an interesting feature. It is alternating. We can better understand this characteristic if we study the coil's rotation. Note that the particles flowing through the circuit represent electrons, but keep in mind conventional current flow is opposite in direction. By looking at this simple generator, we can see most current is produced when the conductor passes through magnetic lines of flux at the fastest rate. That is, the greatest current occurs when the conductor moves at right angles to the magnetic field. Then, as the conductor continues its rotation at a constant speed, it cuts through fewer and fewer lines of flux, and less current is induced. Eventually, the conductor moves parallel to the field. At this point, no current flows because the conductor doesn't cut through any lines of flux. This occurs twice in each revolution. Notice, as the coil rotates, one of its sides cuts downward through the magnetic field, causing current to be induced in one direction, while the other side is moving upward, inducing current in the opposite direction. After the coil passes through the position of no current flow, the previous downward side moves up, and the previous upward side moves down, thus reversing the current flow in the external circuit. This, then, is alternating current, a flow of current in a circuit that reverses direction periodically and is continually varying in magnitude. We must find a way to maintain current flow in one direction in the external circuit. To do this, we need change only the slip rings, which collect alternating current, to a commutator which will rectify, that is, change, AC to DC. The commutator is a collar divided into segments, insulated one from the other. We attach one end of the coil to one of the segments and the other end to another segment. Now, as the coil rotates through the first half cycle, the induced current of one direction is collected from the commutator segment. It flows through the external circuit, then back to another commutator segment and into the coil, completing the circuit. The brush that connects the commutator to the external circuit breaks the contact with the first commutator segment and makes contact with the second. As we've seen, the induced current in the rotating coil is opposite in direction from that of the previous half cycle. But the commutator switches the coil connections to the opposite side of the external circuit. In the external circuit, the current generated from the second half cycle is in the same direction as that generated from the first half cycle. The commutator has rectified the current, converting it from an alternating current to one that flows only in one direction, direct current. But there is a problem. The direct current produced by a single coil is pulsating and unsuitable for most applications. Therefore, practical generators have many coils and many commutator segments that can produce a voltage that pulsates very little and is usable.
So here we have seen, so to be precise, what we have seen now, so here he has uh, considered simple loop generator as we have seen previously. So here this is one conductor and this is one more conductor, that is the coil sides we have assumed A, B and C, D. One is under the influence of north pole and another is under the influence of south pole, and AB conductor or coil side is connected to copper commutator segment C1, whereas the other segment C2 is connected to the conductor CD. Okay, so one coil is connected to point P of the load and other one is connected to the point Q of the load. Okay, so the current direction is from Q to P. So this is in first case. AB conductor was under the influence of north pole. So now when the same conductor comes under the influence of south pole, you can observe the commutator segments. C1 was connected to AB, C2 is connected to CD. Okay, after 180 degrees rotation, you can see clearly from these two figures, along with the coil, commutator segments have also rotated. Okay, so due to this commutator rotation, the current direction will not change. Okay, even though the current has reversed, but along with the current, the commutator segments have also gone through 180 degrees. Okay, so the commutator has reversed the connection of the load. So previously you see the connections to the load. C1 was connected to P, C2 was connected to Q. Now in this diagram you can see C1 is getting connected to Q and C2 is connected to P. So the load, the connections of the commutator to the external load has also reversed. So apart from current direction being reversed, the commutator segments that are connected to the external load terminals are also reversed. Hence, what we can conclude that the direction of the current through the external load is remaining same. Okay, so this is how the commutator plays a very important role to convert the alternating EMF to unidirectional EMF. If the commutator would not have turned along with the coil, then the output of the coil will still be alternating in nature. Since along with the coil, the commutator segments have also rotated, the direction of the current in the external load will remain same. So that is what we should remember in this action of commutator. Okay, so from the diagram you can see that here the output of the EMF generated when we have commutator also rotating along with the coil is pulsating in DC. This is not purely DC, this is pulsating DC, as you can see. So this is not very suitable in many industrial applications. So hence in order to uh, get almost equivalent DC voltage, very number of armature coils are added. The average current passing through them will give almost a DC voltage or the unidirectional EMF. Okay, so this concludes my today's lecture on the working of DC generator and how a commutator is playing a very crucial and important role in the working of DC generator. So until we meet in the next lecture with some other topic, take care, goodbye, thank you.